The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so as Steve gave us an introduction, myself, along with Catherine, David, Nicole, and Charlotte, are excited to present for you guys probabilistic and infinite horizon planning. To give you a brief overview of what we're going to talk about, we're going to start with a quad rotor motivating example. We're going to move into planning with Markov decision processes, give you a little bit about value iteration before discussing heuristic guided solvers. From there, we're going to go into the more stochastic case, partially observable Markov decision processes, and operating in belief space. So, we very often now see quad rotor motion planning as a problem given, for example, with the Amazon Fulfillment Center. We start with a goal configuration, a start configuration, a set of actions we can take, and some type of reward function or cost function. So, for instance, if we have a quad rotor starting at the Amazon Fulfillment Center and we want to get it to 77 Mass Ave, and let's say we want to take the shortest path to get there, we would follow the red dashed line. But as you can see, it comes very close to these obstacles. So we're looking at very high risk for mission failure, crashes. If there's any uncertainty in this path, we're going to have a problem. So one of the ways that we can sort of compensate for that is we follow something like the green path, which is adjusted to give us a little bit more space. Anybody have any questions? So as you can see, the level of uncertainty sort of allows us to determine how easy or difficult a problem is going to be to solve. On the easiest side, we have deterministic dynamics and deterministic sensors. In this case, our actions are going to be executed as commanded, and our sensor is going to tell us exactly where we are. This would be something like dead reckoning validated through sensing. Very redundant. If we move into a little bit more of a difficult case, we have deterministic dynamics. Our commands are still being executed, but maybe we have a noisy camera, so we have some uncertainty in the sensors. These are the cases where we would see dead reckoning, but we would compensate with common filtering, sort of get rid of that noise level. Now, down at the bottom, sorry, what is dead reckoning? It's essentially you are saying, I want to execute this action, and it's going to execute it exactly. Okay. Then towards the bottom, we have stochastic dynamics and deterministic sensors. So in this case, maybe there's some uncertainty in our actions, but we can validate through sensing. This is where we're going to spend the next section on Markov decision processes. And then briefly, later in the lecture, we're going to talk about this most difficult case, which is the stochastic dynamics and stochastic sensors. Our execution, maybe, maybe not. Our sensors, maybe a little bit of noise. And this is where we see partially observable Markov decision processes.
Let me make just a quick clarification on the dead reckoning. So dead reckoning is where you estimate your position using a probabilistic model, but you don't use any observation stuff in that estimate. Okay, so we talked a little bit about action uncertainty, where we're going to focus. And this is the case where, for instance, even if you tell a quad rotor to stay in its place and a gust of wind comes by, it's not going to stay in that same place, right? It's going to have a little bit of movement. And we can see this causes things in this disparity, where you have a commanded trajectory and your actual trajectory, and they begin to dissociate. So in order to compensate for that, we want to model things with that uncertainty, or else we have these higher situations where we command to follow some line, we don't incorporate the uncertainty, and we see a crash. So this allows us to introduce planning with Markov decision processes. So MDPs have a set of states, a set of actions you can take, a transition model, so essentially what's the probability of reaching some state if you take an action, an immediate reward function, and a discount factor. This discount factor is important because it allows us to prioritize gaining an immediate reward as opposed to an uncertain future reward. So the concept of bird in the hand is worth two in the bush. Now, we want to find an optimal policy that will essentially map an action, the best action, for each state. And what we hope to get from this is a maximized expected lifetime reward. So we want to maximize the accumulated reward we get over the time steps. So let's walk through an example. If we have a quad rotor perfect sensor, and let's put it in this environment where we live on a 7x7 grid. Our set of states are obviously the grid spaces. Can anybody tell me what some of the actions might be? Yep, up, down, left, right. In this case, we call them north, south, east, west, or null.
Next thing, we, for this example, arbitrarily gave ourselves a transition probability. So we said that you have a 50% chance of following your commanded action with a 25% chance of moving to the left or the right. Next, we have the reward function. And again, we arbitrarily decided that we want it to be a reward if you get to state 6.5, that you increment a reward of 1. Go ahead.
When you say you have a 25% chance of moving to the left or the right, is that like clockwise and counterclockwise of where you plan to, or like let's say you plan to go to the right, would that mean that you have a 75% chance of going to the right and 25% chance of going to the left, or like it'd be this way and 25 up and down?
We said clockwise, counterclockwise from the intended direction of action.
Okay, thanks.
And finally, we gave ourselves a discount factor of 0.9. So let's assume for a second that we have our optimal policy. And let's say that our optimal policy says from this state we want to take the action north, right? As we discussed, we have a 50% chance of going north, and a 25% chance of going to the left or right. So after that time step, these are our possible states that we could end up in, right? So now let's assume for a second that we can take our next action, and our next action says go north. Again, we have the same probability distribution, and now these are the states we could end up in after 2 time steps. We can see that this starts getting very complicated, right? And there are increasing amounts of uncertainty. So, does anybody have any ideas on how we could sort of collapse this distribution? Keeping in mind that our sensors at this point are deterministic. Yeah?
Fly to a corner.
I'm sorry?
Fly to a corner.
We could do that.
And you just sense how far away the red block is.
We could do that.
Quick comment.
Yeah.
So the belief state does not add you 1.
I'm sorry?
So the probabilities do not add you 1.
Yeah, the issue is if you went to 1.3 and then you transitioned to the left, that's where the extra 0.0625 is coming from.
Oh yeah, but shouldn't those numbers always add you 1? I mean, your probability distribution always has you add you 1.
Yeah.
So it's a point.
It's just off the screen. So you should.
We would add another section to the screen and just move the grid over.
Okay.
We just cut it off for these little graphics.
Okay.
Yeah, so those are all great points. The easiest way to do it is just to take an observation. So at this point we say after our first time step, we weren't sure which of these 3 states we were in, so we took an observation and said, wait, we're actually here with complete certainty. So to make this a little bit clear, we're going to look at it from a tree view, right? We said that we started in the state, we took an action, and this is our possible states we could have ended up in. We're going to collapse this by taking this observation, and now we have a complete certainty here, and we take our next action, and see that we have moved out here. So this allows us to basically ignore the history of states. We have the same percentage probability from each time step. This will be really, really useful in completely collapsing the distribution every single time we take an observation. Anybody have any questions about that? Okay. So let's go back now and figure out how we came up with this optimal policy. The way we do that is through dynamic programming. There's 2 different ways. You can do it either through value iteration or policy iteration. For this lecture, we're going to focus on value iteration. So let's take the same example we had. We still want to maximize the expected reward. And so to start, we're going to initialize the values of each state to 0. Now, let's, for example, start T0. We're going to focus on state 6.5. And we're going to say that we're going to take the null action to start with. From there, you can see that the probability distribution for 6.5, we have a 50% of staying there. We have a 25% chance of going to 5.5 and a 25% chance of going to 7.5. The next set of information is the values in each of those states that we could end up in, and currently they're all set to 0. And finally, the most important part here will be the reward for being in 6.5, taking the null action, regardless of what state we end up, is going to be 1, as we defined in our initial setup. So let's see how we would calculate the next time step value of the state. We'd start by taking the probabilities, right? And from there, we would add the reward here. And because we said that the reward is not dependent on the state we end up in, we want to distribute across all 3 probabilities. From there, we're going to add in the discounted value that we had from before. So a way to look at this in a more generalized form is to say that across all the states that you can end up in, you're going to look at the probability of ending up in that state, and you're going to multiply that by the sum of the reward and the discounted lifetime value that it has. So we want to make sure that we're getting the best possible value. So we need to incorporate all the other actions that we can take from that state. So what's going to happen is we're going to take that general formula, we're going to repeat it over all of the possible actions, and then we're going to take the maximum of that. So for this example, this state is very easy. All of them are the same for this case. But we go across and we see that we get a value of 1. And we update it as shown in the graph. This gives us what's called the Bellman backup or update equation. This will be really important because it reaches across the entire state space and allows us to provide a history. So what this would end up looking like is we're going to iteratively calculate the values across the entire state space. So at t0, we determine that all the values are 0. At t1, 6, 5 gets a value of 1. And at t2, we see that value start to propagate out. Makes sense so far? So the way this works is you would repeat those iterations until your changes in value become what we consider small enough, which would indicate that your approximation is close enough to the real value. From there, you would extract the optimal policy from the lifetime values, so you see the same Bellman equation, and you're now just taking the action from it. And you would map those actions to your states. An example of what this might look like propagating out, if you say blue is the reward, and red is an obstacle, etc., you can see as that value propagates out, and you start seeing your policy by the arrows. Anybody have any questions? So one last thing to mention about this, though, is that the complexity for each iteration is dependent on the size of the state space squared and the number of actions you can take. So you can imagine as your state space expands, or you gather more actions, it starts getting very complex, in which case value iteration becomes very time-intensive and costly. So this allows us to move into heuristic-guided solvers.
So transition, one quick question. So how many, can I just get a show of hands? How many of you have learned value iteration before versus how many have seen it for the first time? So how many have seen it before? Okay, and then how many is this the first time? So it's not too many. Okay, good.
Okay. Any questions on value iteration before we jump in? It's going to be an essential part of how we're going to do heuristic guided solvers. Anyone who hasn't seen it before? Okay, cool. So the most important thing we said about value iteration is that it's super slow. It's going to have to go over every possible state and every possible action we could take. Our state space is multidimensional and we can take a lot of different actions. That's going to be really costly and really hard to do. So what the approach we're probably going to want to take is using some sort of best first search algorithm. Who can tell me some example algorithms that already do that? A-star. So that's very good, and that's exactly what we're going to base our stuff off of. The A-star is for deterministic graph search. If we have a graph, we can use a heuristic, and we walk down it and search the space that we're most interested in to get to our goal. Very good. So we're going to introduce two new algorithms focusing on the last one. AO star is an algorithm we can use to search for graphs that have this sort of AND coupling. AO stands for and/or graphs, as opposed to the simple graphs that we used to. The AND is kind of a way to express probabilistic coupling between edges. So if we explore one thing, we might have to explore other proportions. We'll discuss that a little bit more in the next slide. LAO is a bit more of a generalization. What it does is allows us to search loopy graphs and deal with the probabilistic coupling, and allows us to search and find the best path with a heuristic guided algorithm over an infinite time horizon, possibly revisiting states and using the tools we just had in value iteration to understand what the next best thing to do is. So we'll talk about exactly how to get from MDPs that we just saw, these whole arrow examples, to these sort of and/or graphs. We'll talk about two cases. One simple one where we could apply the AO star algorithm is where you have a quadcopter. And if you command an action north, you have a high probability of going north, but you might go east. and vice versa. If you go east, you might go north. This is expressed here with this growing tree and these and edges that connect. But despite the action that we might command from 0, 0, we might end up in 1, 0 or 0, 1, right? And as we propagate outward, you can see how we're never going to loop back to a state that we've been to. We're going to be moving in the northeast direction constantly. And our tree expands, and our probability distribution across this tree expands. And that's the coupling of the edges, because as we explore down the tree, we have to explore all the edges together. Anyone have any questions on just this kind of conversion of this formulation?
I have a broader question. We mentioned that MDPs deal with finite states. Do we always just discretize the continuous world into a set of finite states?
Yes. That's kind of a prerequisite for searching over the state space. We can do that as finely as possible, but yes, discretization is there. Cool. So now let's look at this case. Instead of the northeast, let's say it's not deterministic whether we command an action north or south, whether we go north or south. Here we see this loopy structure begin to emerge. We see that we might, on our first action commanding north, we might go to +1, and then commanding north again, but we have our and edge and our probabilities distribution might say go back to 0. What this does, it creates this loopy structure. This is exactly what we're going to be exploring. This is a very real-world scenario where it's very likely we might return to somewhere we just came from, just because of the uncertain dynamics we have. So this is the type of problem we're going to solve. So we're going to use the LAO star algorithm. We're going to talk about the three main things that it's good for. It has a heuristic guided envelope, and what that means is that we have our large state space here, but we're only going to look at a portion of it, this grayed out portion. We're only going to look at the portion that is interesting to us, the portion that provides us with the biggest rewards, the portion that's reachable if we follow an optimal policy. We figure this out with some admissible heuristic, with overestimated costs, overestimated rewards, just like A star. The idea here was that we'll keep the problem small, so we don't have to search with value iteration over a giant state space. What we'll do next is, as the state space expands and we get a bigger picture of the states that we're interested in, we're going to do value iteration. We're going to figure out what the best action is, and in the ideal case, the states that we would never reach using an optimal policy are never going to be explored, because our policy is going to say, no, don't go over there, that's a dead end, or that's getting you farther away from the goal. So we're going to be searching in a very specific part of the state space that is useful to explore, that will get us closer and get us a higher reward. What's important here, the L stands for loops. It's an extension of the AO star algorithm, which itself is an extension of the A star algorithm. And we can handle infinite horizon problems that can transition in different ways, and really models kind of the real world scenarios we're interested in. Any questions so far, and kind of the broad scope of what AO star is going to do?
Can you quickly go over again with the OB? I know you kind of briefly went over it, but I didn't quite.
Sure. The AO stands for and/or graphs. So that's graphs that we have here, edges that are coupled, that if you attempt to do this transition, you might end up here or you might end up there. So that's the notion of this probabilistic coupling that we'll see in action as we start walking through the algorithm. Alright. So for our algorithm, what we're going to do, we're going to input this either an MDP or an AO graph with transition probabilities or reward function and heuristics. These are all things that we kind of defined prior to figuring out a plan. What we're going to come out with is an optimal policy for every reachable state. It's a little different than what value iteration gave us, which is an optimal policy for every possible state. But we argue that that's all we need. That if we know where we're starting and we follow our optimal policy, we're only going to explore a certain portion of the subspace. And we're going to exploit that to get an infinite horizon plan a little bit more efficiently than iterating over a high dimensional state space. Any questions so far? Good. So we'll define some terms that we're going to use throughout this. We've already talked about our state space. This is just a small portion of it that we're going to work with as we're going to walk through this example. Next, we're going to define something called rectangle, and that's the sub-portion of our state space that we're going to be looking at. We're going to initialize that to just S0, the state that we set. But as we progress through the algorithm, it's going to grow. And it's going to grow only to the areas that we're interested in. A subset of this envelope is the terminal states. Now these aren't goal states, these are just the leaves of our space that we've added to our envelope. So this is what it would be in the expanded implementation. It's just the nodes that haven't been expanded yet. Here we haven't drawn anything further, but you can imagine the state space goes out further because it's sitting on the horizon. You can imagine that this goes out further, and we're keeping track of the nodes that we haven't expanded yet. Or likewise, we showed that we're going to initialize that to just S0. The other few things that we're going to define, we've already defined the states that are in our envelope, that's the blue or the red. We're going to define a cost or heuristic or reward function, RE, and a transition probability matrix or set of matrices that we're going to use our optimal policy search on. What's important here is that our reward function and our transition probabilities are slightly altered to account for the fact that we haven't explored the entire state space yet. We see here that if a node is an ST, in other words, it's one of those terminal edges, terminal nodes, we're gonna say we can't transition out of it because we don't know what's beyond it so far. And we're gonna set its reward to be a heuristic, whatever we think that the reward is going to be when we begin to explore it and go further. And like I said, we're just going to feed this into a policy search, just like we discussed with value iteration, and on this subproblem, and we're going to search for an optimal policy on this end. So far, so good? These are the general steps. This is very texty, but we're going to definitely walk through every single step. We're going to do 2 full iterations of that. So like I said, we're going to create our RE and TD. That's our reward function transition probabilities using the definitions we showed. We're going to use value iteration to find the optimal policy on the subspace that we're interested in now. And then we're going to, this is probably the most important step. Knowing this optimal policy, we take a look at what new states that are in our terminal states, nodes that we haven't explored yet, what new states we might visit now. So let's say we have our policy and it says that we go north, and we know that we haven't explored the north state yet. We know this is the state that we're going to reach following what we consider now to be already an optimal form. So that's the states we're going to expand next. We're going to do some bookkeeping, adding them to the terminal state set, and then the ones we expanded, and adding them to our envelope. What's important here is that we're only going to add states that we haven't visited yet to our envelope. And this is basically the little hack that allows us to deal with loopy graphs. We're not going to continually explore nodes that we might reach a second time probabilistically. We're going to let value iteration kind of handle that and iterate over that to give us the best.
Can we say repeat until node states are expanded? I'm a little confused on that. Like, are you saying that you're going to just repeat until there aren't any like terminal states we go look at? And if that's the case, how is that possible if you have like an infinite horizon so you can walk around?
Sure. So you can imagine, and we'll talk about termination in depth at the end, but you can imagine that as we have these terminal states, but you have a policy that guides you to a part of the state space that you've already expanded. Imagine you've reached your goal, your optimal policy is going to say stay put, right? And it's not going to say move north again.
It's just the goal state.
Essentially, the goal state is definitely an example, or in the more extreme case, if there's nothing else you can do that's going to get you closer to the goal. Right? So the idea is that that your policy on your subspace never tells you to go to a terminal node again. So they're inherently worse than you are already.
Finding the optimal policy means running value iteration entirely.
Yes, we're going to treat it essentially as a black box. But the trick here is that we're doing it on a smaller portion of space than we did before. All right, I'm going to put the steps up there. Hopefully you can sort of see this. But for now, we'll just kind of walk through from the beginning of what we're going to do. So we said that our envelope and our terminal nodes are just S0 to start. So very simply, we use these definitions and say, okay, the transition probability out of S0 to any node right now is 0 because it's in our terminal node set. That's just so that we don't transition out of it. We can develop a policy based on only the portion of the space that we don't have. And our reward function, we're just going to apply it to be the heuristic of S0. Let's say that's 20, and we're going to move on from there. We'll pass that into value iteration, and we'll run this value iteration. This is a very, very basic case. We're using this to kind of build up machinery and understand what we're doing. It's a very basic case where the only node we have is S0. We can't transition out of it. All we have is some heuristic. So the only thing we can do is nothing. So the action we're going to take from S0 is nothing. Very simple case just to kind of get us warmed up and understand what's happening. So using this policy and knowing that S0 is in our terminal node set, we're going to take the intersection between this terminal node set and the nodes that we might reach following our policy. Now we know we're at S0, and we know the only action, the action that our optimal policy says to take is none. So we know we're there. We know it's in our terminal node set. So that's the only thing that we can reach so far using our optimal policy. So far, so good. Clear? Oh, so that's exactly what we're going to expand. We're just going to expand S0 to A, B, and C, and add those to our terminal nodes. So that's up there, just simple, but we removed S0 from our terminal nodes, added its children, and we added the children to N. Now here we go, we're going to get a little bit more interesting. We're going to do the same thing again, but now we obviously have more nodes and a bigger subspace to explore on. So using these definitions, we see our reward function is a tuple of the node that we start from, in this case S0, and one of these three actions. So we take A1, A2, and A3. And we have our instantaneous reward functions, 6, 4, and 8, as being our rewards from taking those actions from S0. From A, B, and C, no matter what action we take, it's just a heuristic, because that's part of our definition. And likewise, we're going to take a look at this transition probability matrix. This is for transitioning from a state S0. We're saying if we take actions A1, A2, and A3, what's the probability we end up in nodes A, B, and C? If we look so far here, we're going to look at something deterministic. So if we take an action, we'll end up where we say we're going to end up. And we'll see how this algorithm sort of collapses down to A star if everything is deterministic. We're also obviously going to look at the probabilistic case where we say move A1, but there's a small probability that we might end up with B. That's going to necessitate that we're going to have to look at and expand B together with A if we were to decide we want to try it with A. And likewise, if we try to take action A3, we have to expand all three nodes. So the tighter the probabilistic coupling, the more of the space we're going to have to explore. So just off this, assuming that if we take action A1, A2, and A3, what could someone tell me what the policy is? We have the rewards here, and we're interested in a policy from S0 and what we're going to do. Take a minute to take a look at the rewards and sort of just judge what the best action to take is in a purely deterministic sense.
When you're determining the rewards, do you add like 6 and 15, or do you just look at
You add the reward that you have gotten so far.
to the
Yeah, to the heuristic. Does that help you answer the question?
Oh yeah, I think you should throw this data in.
Perfect. So the policy definitely says from S0 take action A1. And that's going to stay A. And just for bookkeeping, from A and C, there is no action to take, so we're going to leave those. What that means is that the nodes that we might reach that are in our terminal state set using our policy is node A. Right? So that's the node we're going to expand. And this is where you really, really see that all we've done is collapse down to A star and just deterministic case. A star would say, okay, let's look at the best node using some heuristic. Action A1 takes us to that best node, and we're going to kind of expand just that node and repeat the nodes. So when everything's deterministic, basically this algorithm collapses down to A star, and nothing super interesting. The interesting case does come up when we start doing more probabilistic things, and that's where nodes are probabilistically coupled in this AND graph sense. So now we have our policy. The policy is likely going to remain the same because we have very little probability on on the edge actions that we might accidentally end up in, and nodes that we might accidentally end up in. So what I want to take a look at is what nodes are now reachable following our optimal policy. So we talked about that if we were to take action A3, we have some probability of ending up in any of the nodes. So taking action A3 makes C, D, and A all reachable. What's reachable if we take action A1?
A and B.
Perfect. And that's where we get the notion of this probabilistic coupling, where we're going to have to expand things together, explore the part of the state space that we reach both our optimal policy and that we might accidentally end up in if we still follow the optimal policy. And this is what guarantees that we'll have an action to take from any state that we intended to go to, or that we might end up in probabilistically. That's how our state space expands, our envelope expands to encompass only the reachable and interesting states that we want to look at. It's not as simple as just expanding down with a heuristic, like with A star, because we have this probabilistic coupling. And you can see that if you have a tighter coupling, then you don't get to exploit this optimization as much. So for example, in A3 we would have had to expand all three nodes, as opposed to A1, we can just stick to A and B and ignore expanding C for now, because our policy won't reach us there. This is
Quick question, about the heuristics. When people do the t-statistics, right, they have like a significant level. So in this case, if you take the action A, you go to A and B, the probability rewrite, do you think it's a good heuristic that we can prune the B, just search for A? Because they have a very high probability at A in this case.
So in the complete sense of running this algorithm, we shouldn't prune it, because what if we do and we have that 2% chance we do end up there? We need to have a policy for correcting, right? So we end up in B. You can imagine that B is going to try to push back to whatever path that A was looking for, right? I suppose if the probability is low enough, you can have some sort of cutoff percentage where you decouple the nodes and you don't expand.
So just a quick point. So I think that's an excellent point and an excellent answer. We're going to talk about next week exactly what's going to happen if you can prune sort of lower probability events. And actually, paper right here will be lecturing on that. So. Good question.
That sort of also gets us into the sense that if kind of every state in the world were probabilistically coupled, let's say we had some transporter to go with the Star Trek examples. If we had this transporter that non-deterministically put us in any state in the world, we'd have to explore the whole world because we could end up anywhere. So luckily that's not the case yet. We can kind of take advantage of the fact that we might only end up in most likely where we command and with some probability in the states nearby. This is exactly what we just talked about. We couple these nodes with this AND edge, and we expand those two. And just everyone understanding both the intuition and the logic for why both of them have to be expanded, even if there's only a small probability that we end up in B. So this is what we're going to repeat until there are no states to expand. You can imagine that the next time we run our value iteration, we're now running it on all of these colored nodes, both the blue and the red. We can imagine that next time, now that we have a little bit more information, what lies beyond A and B, that our policy might say, oh, you know what, actually, from S0, C, like action A3 was the best to take. What that does is say, okay, what's reachable now? It's A, B, and C. And we expand those nodes. But we've already expanded A and B, so we kind of move into the next part of the subspace that as we gain more information, we run value iteration and we can expand down the line. Steve asked a good question when we did our dry run about whether there is sort of a way to save on the computation you did prior with value iteration and add these sort of edge states. And we've looked at it a little bit. I've seen some stuff, but not. I haven't found a paper that specifically deals with it. But you can imagine how you've already run value iteration on your previous iteration of this group, and you add the new terminal edges that you've expanded, and you run it again until it stabilizes. And that way you've saved the computation having to run valuation multiple times on a growing state space.
So I'm trying to think of how this is different from something like enforced hill climbing for FF, so like FF-based heuristic search.
I think, no, I don't know enough about that, but my kind of basic understanding says that what's useful here is kind of it's this explicit probabilistic problem. I don't know how much that deals with.
And also, as long as your heuristic is admissible, it's guaranteed optimality with not all hill climbing algorithms. But, right, just like A star is optimal as long as you've got a consistent admissible heuristic.
Alright, so that's definitely the idea here. We couple these and we only explore the portion of the state space that we'll reach using an optimal policy. We do have some guaranteed optimality. So we'll talk about quickly kind of determination. We've touched on most of this. So it's most likely when there are no more states to expand, it's when we've reached our goal. It's when our policy that we run on our entire envelope from value duration doesn't say that we should go to any more terminal values that we haven't looked at yet, that we haven't expanded. We've said that those are only the things that are reachable and needed, both reachable because we're following an optimal policy, and needed only if we might accidentally end up in a probabilistic. This gives us the sense of completeness, that we get a policy on the entire state space that we can end up in following an optimal policy. Yeah, the third bullet here kind of touches on if we don't expand the states that are probabilistically coupled and we do accidentally end up there, we risk getting lost and not having a policy. We can compute this all offline and have a plan before we even start flying to know exactly where we want to go, even if our dynamics are not deterministic. We're going to come back to this. This was our motivating example. And so we show that these real platforms can be modeled stochastically, and then we can pretty easily deal with that. We can just search our state space and deal with those probabilities and expand the nodes that we might end up in, right? And that heuristic allows us to not have to explore this area of the state space because we might never actually end up there. We'll always be commanding toward 77. That's out. We're never going to try to command backward. Sure, if there's a gust of wind and we have some probability there, but you can imagine that we'll only explore a small portion of this because we'll always be trying to correct to get back to these optimal paths. And with using our reward function, we get to determine if we want to fly a quick path or if we want to fly a safer path. For example, our time times our probability of collision. We want to perhaps reduce that.
All right. Are there any questions about planning with MVPs? Anything like that? I love this stuff, so the more questions, the more I get to talk. Fine. What I'm going to be talking about for the rest of this lecture is extending beyond MVPs to a broader class of problems called POMVPs, partially observable Markov decision processes. I love this stuff. I think it's really cool. They're really fun problems. We're going to talk about, though, why they're so much harder to plan with, to execute, but why they're important to at least know about so that you can model real-world problems with them. And then we're going to delve into a case study of a specific POMVP solver. We're not going to go into as much detail as we did for MVPs, but we're going to look at what powerful results you can get by planning with POMVPs. So first, I want to reframe this in the overall talk. Right? We have this spectrum of uncertainty, and coupled with uncertainty is difficulty of planning, of solving, of executing a problem. And we've killed these first two cases. That was really easy. And then we just discussed the bottom case, MVPs. What I'm going to talk about is the case when both your dynamics and your sensors are stochastic. And why is that important? It's because when we first saw this slide, our motivating example slide, we only saw the left-hand side. We said our actions are uncertain, but good news, we have a perfect sensor. We have a perfect camera. But that's unrealistic. I think we've all, to some extent, experienced the fact that no sensor is totally perfect. Your camera might have fluctuating pixel values. Your laser rangefinder is going to never read out exactly the right number all the time. You can have a camera in different lighting conditions that'll behave differently. You might not be able to observe your full state. That's, in a way, an imperfect sensor, right? If I'm in this room, I have imperfect eyes. I can't map out all of MIT's campus because I'm blocked by walls. How can you deal with the fact that you can't see all your obstacles all the time? We've already talked about some cases. There are some algorithms that can help us with that, like D-star light. But can we reason about these things probabilistically? And then finally, you might be in a non-unique environment where you cannot resolve your state with certainty, no matter how good your sensors are. Imagine you're in a building with two identical hallways, you're dropped off in one of them. How can you resolve, how can you figure out where you are? You can't, unless you start exploring. And so, we've got to deal with this uncertainty, right? It's part of every single problem. When observational uncertainty is small, you can maybe ignore it, but it's there. And so, we're going to formulate this as a POMDP, a partially observable Markov decision process. And this next slide is just like the MVP slide, hairy but important, right? We can formulate a POMDP with 7 elements. An MDP took 5, right? Most of them, or all of those, are carried over here. We've got our set of states, where we can be. We've got a set of actions, what we can do. We've got our transition model, which says, given that I started in one state, and then I took an action, what's the probability I end up somewhere else? And like David was talking about, hopefully that distribution is pretty local. We're not teleporting all over the world. We've got a reward function. This is exactly the same as for MVPs. And we've got our discount factor down here. The key difference in the POMDP is these 2 elements. We've got a set of possible observations and a probabilistic model for the probability of making an observation given your state and the action you just took. Now, it's important, I think it matches up really well with real-world sensors, having this probabilistic model. If you have a laser rangefinder, for example, and you're standing 1 foot away from the wall. Now, a perfect sensor would always say you're 1 foot away from the wall, you're 1 foot away from the wall, you're 1 foot away from the wall. Every single reading is constant. But realistically, there might be Gaussian noise, for example. Or, at a more extreme case, it says you're 1 foot away from the wall, you're 2 feet, you're right there. There's this distribution. And so, you would, ideally, you characterize that distribution and you plug that into this model, and that formulates your POMDP. This sounds really hairy, but if we work through just sort of a sample iteration of living in a POMDP world, it's not too bad. You start at some state S, you take an action, A. With some probability, you're going to end up in a bunch of different states based on your transition model. At that point, we can use the lessons we learned from MDP land, where we said when we make observations, we reduce our uncertainty, collapse into a single state. So we say, let's take an observation. But this time, observations aren't guaranteed to resolve all our uncertainty. So we make an observation, and that observation is probabilistic based on our current state and the action we just took. And again, obviously it depends on your current state, because if you're 1 foot away from a wall, hopefully you'll get a different characterization of observations than if you're 20 feet away from a wall. Otherwise, your sensor is totally useless. Are there any questions about this formulation?
Yeah, quick question. So when you take an observation, noisy observation, and then you try to infer which state you're in, is it just kind of a clustering problem? For instance, you know, like the multi-cluster Gaussian, the GMM models. So I mean, class A, class B, class C, which is state. When taking an observation, there's a high probability going to here versus lower probability going over here. Is this what I'm trying to do for each observation over here? So you're trying to find a clustering where does this observation belong to?
So you could, I imagine, implement an algorithm where, yeah, every time you make an observation, you then try to say, all right, what's my most likely estimate? Or maybe my Bayesian least cost estimate. But inherent with that is the risk that you're discarding a lot of information, right? Because you're going to generate a probability distribution over your state. And so, yes, you can say I'm going to stick with the maximum likelihood estimate, but if you can, you you should probably try to maintain that distribution as long as possible. Okay? And we'll see that this is really computationally expensive unless you start making some assumptions. And in the case study we're going to look into, that's exactly what we do. But I've seen a lot in the literature that as much as you can, you want to maintain these distributions for improved accuracy. Any other questions? All right. Well, we're going to compare now the execution of a POMDP to the execution of an MDP. We start out, we're living in the same sort of grid world, we've got our same transition model, everything's peachy. We take action 1, we want to go north, right? We have this distribution that we generate in states. And at this point, what did we say? We said we hate the fact that we have to deal with 3 cases. 3 is too many, so let's make an observation to collapse this distribution. Now, I've described a lot about noisy sensors, right? Where basically it's a true measurement plus some noise, maybe Gaussian distributed. There's another sort of partially observable sensor you can have in a POMDP, which really feeds into the name partially observable. What if you can only observe part of your state? For example, if you're living in an XY grid, maybe you can only observe your Y dimension. This could match up in a real-world example to a quadrotor flying down a hallway. Catherine was working on a project, on a DARPA project with quadrotors flying down hallways. If the hallway is too long, your laser rangefinder isn't going to be able to determine where you are along one axis, but it can tell where you are along another. And so that's what I've said. I've said pretend this quadrotor has that sensor. It can only observe its Y component. And it says, my Y component is 3, no idea what my X component is. Well, this sucks, right? Because we got rid of this state, but then we couldn't decide, are we at state 1-3 or 3-3? There's no way of resolving this, so we can renormalize, we can add in the effects from the observation probabilities, saying maybe, in fact, I'm far more likely to observe state 3 or a Y component of 3 if I'm at 1-3. But in this case, we say it's equally likely to make that observation for those 2 states. And so now we've got to deal with these 2 cases. And so when we take our next action, instead of resetting to a single state, we've got to keep growing this tree. And what's the key difference between this and when we were executing our MDP? It's that we didn't manage to collapse back to a single state. We didn't manage to reset the problem. And this is, annoying because you can't execute a policy and say, I'm certain that this is my configuration. So your policy can't map from exact states to actions because you never know your exact state. Does this make sense? Has everyone lost hope in planning, right? Yeah.
So in here, because so from the left to the right,
yep,
you're basically mapping from one belief state to another belief state. So it's kind of like a one arrow thing. But and then from that second layer, you should have 2 arrows. One with probability 0.5 that observes 3, and that gives rise to that belief state I just showed. And one with probability 0.5 where the sensor is reading 4. Because if you have non-zero probability of being a true 4, you might as well just observe 4 as well as your Y. So in this case, I mean, I'm not sure if you were just trying to show one branch of your POMDP planning, but basically what you have to do is you would go from this to the second layer. You would have a branch with just 0.5 probability on either, one giving you 3, one giving you 4. For the one that you showed, you get a belief state. For the other one, you get the state 2-4 with probably 1. Right?
Yeah. So you were perfectly describing planning, right? I should have made this more clear. This isn't planning, this is executing. We have this policy that we're going to execute. And so if we were planning, we would have to consider all these branches and say, well, I could take, there's a 50% chance I'll end up here, in which case my Y value is going to read 4, you're going to have to grow this whole thing. I'm saying, no, this is real-time execution. Yeah, great question. Any others? Well, this is a great time to transition to, well, we can't just magically be handed these policies. How do we actually generate them? How do we start planning in the belief space? The belief space, right, is a space of distributions of possible configurations. So I'm going to talk about a sort of general class of algorithms. A lot of planners in POMVP land, in the belief space, plan with probabilistic roadmaps, PRMs. Right? The goal is to generate a policy that maps from a belief statement to an action. And I'm going to go into a little more later what a belief statement is. But the general algorithm, and this graphic illustrates these 4 steps, is we're going to sample points from the configuration space, right? As if everything was deterministic. We're going to connect those points to nearby points. You can define nearby however you want. It can be your k closest neighbors, all neighbors within a radius, whatever, as long as those edges don't collide with obstacles. Once you've done that, somehow, and there's some magic in this, you're going to transform your configuration space probabilistic roadmap to a probabilistic roadmap in the belief space. Great. Once you've done that, you can just do shortest path depending on whatever cost function you use. And what's really cool is you get different shortest paths for when you stay in the configuration space and when you go to the belief space. So the green path, that bottom right figure, seems a lot longer than the red path. And the reason is the green path was planned in the belief space and followed a lot of landmarks that the quadrotor could take measurements off of. So it was really confident about its position, whereas the red path is the shortest path that had a higher likelihood of a collision. So we're going to look into that figure more later. I'm going to segment this algorithm into 2 parts. The first part, these first 2 steps, it's just probabilistic roadmaps. Who here has heard about probabilistic roadmaps? Raise your hand. Okay, then 50-50. I'm so excited for the 50% who haven't heard. One of the top algorithms, in my opinion. It's really simple, and it's really powerful. Here's basically almost a complete implementation of probabilistic roadmaps. It's pseudocode, so don't copy-paste, but it's almost there. Right? You're going to construct a graph. It's empty. You're going to add your start goal, or your start configuration, maybe the green dot, and the goal configuration, the red dot. Then you're just going to keep sampling nodes from the free space. You say, how about 2 free? You're going to add that to your graph. You're going to connect that node to a bunch of other nodes nearby. And then you're just going to keep sampling, until maybe you have enough nodes, or maybe until you have your complete path, which should be happening there. And then once you've got this whole graph, you can just find the shortest path along that. And there's some really cool results that if you sample like, in a good way and so on, asymptotically, as you start sampling more, you're going to asymptotically approach the best path in a completely continuous space. The power of probabilistic roadmaps and a bunch of randomized algorithms, though, is that they scale pretty well to high dimensions. So you don't need to actually consider the continuous space. You can just sample a bunch of points. Are there any questions about probabilistic roadmaps? They're really cool. If you're interested and you just heard about PRMs, you probably haven't heard about RRTs. Those are also really cool.
Just a quick question.
Yeah.
So for any node, if I want to sample, I just uniformly sample the node around them, just randomly choose one uniform with a uniform distribution, right?
Sorry, when you're choosing where to place a dot or what to connect to?
There's a dot there, I'm deciding to expand and sampling, right? So when I do the sampling, I just print this node, I just uniformly choose one of them around it, then start doing the expansion, or there's something else.
So, in general, probabilistic roadmaps, you can throw in whatever sampler you want. The way this particular one, the way I implemented this, is you sample points uniformly from the entire space. If it's inside an obstacle, you remove it. Once you place it, this was connect to the k closest. I think k is 7 in this case. I don't know. And if there's an edge if that edge collides with an obstacle, remove it. I'd be happy to go into more details about PRMs later. All right, but that's not enough, because what we described was PRMs in the configuration space. But what we need to do is somehow elevate a PRM from the configuration space to a belief space. And this is really hard. We don't have access, right, to these raw configurations. Let's imagine we were in this really simple world where the quadrotor could be in 3 possible states. 1, 2, 3. Really easy, right? sample a bunch of points, they're going to end up in 1, 2, or 3. You could pretty quickly cover the entire space. But this simple configuration space, when transformed to the belief space, becomes infinite. You have infinite possible distributions to consider. There's the distribution where you have 100% chance probability, 100% probability that you're in state 1, 100% probability that you're in state 2, 100% probability you're in state 3, and then everything in between. Right? We went from 3 to infinite. This is not boding well. And even if you start saying, well, I'm not going to consider the whole distribution, I just care about like the mean and the variance, it's still not pretty, right? Well, this is where we have to start making approximations, and this is where you start getting differences in POM-DP planners, where they make assumptions, where they make approximations. So these images are from the belief roadmap paper from the Robust Robotics group a couple years ago, but I'm going to talk about a different planner soon. But the idea behind a lot of these planners is maybe we can start saying what these distributions are going to look like based on our models, right? So to our planning problem, if we know we start at 2, 3, and we know our transition distribution, we can start saying, well, this is my probability distribution. And then when I make an observation, I can build distributions off that. And so if you could exhaustively just sort of propagate these distributions forward, that would be great. It's unrealistic. And I just want to point in terms of a visual way to represent these distributions. A really nice way is saying, in the deterministic world, right, you have these dots and edges. In the probabilistic world, these sort of circles, these ellipsoids, represent the uncertainty. Typically, it's like 1 standard deviation or 3 standard deviations away. And so you can start, building into the map. These are the distributions and the variances I can see at these nodes. Are there any questions about this sort of stuff? All right, well, we're going to delve now into a specific case study, feedback-based information state roadmaps. Firm, from now on, that's all. Only way I'm going to refer to it. The idea behind this is you're going to sample mean configurations from your configuration space. Then you want to build an LQR that's linear quadratic regulator controller around these mean points, and that'll generate what variance you can tolerate. Right? So LQR controllers, if you don't know, they're really nice. They in a small region around a point, they can drive a quadrotor, for example, to that configuration. And so if you build these LQR controllers around points, you can say, all right, anytime I end up in this cloud, right, this cloud in the belief space, so any sort of distribution, I can bring it back to that mean. And so now what we've done is we've generated every point, we just need to connect them. And the idea is if you have a feedback controller, feedback-based, that can get from one cloud to another anywhere in the clouds, then you can get from point to point. All right, this is how you generate the graph. And what's cool is the way they formulated the problem. Is they said, well, set up the cost of executing an edge. We switched from rewards to costs because we're pessimists now. Hey, well, the cost is going to be a linear combination of the expected time to execute that edge and the uncertainty along that edge. Now, this is actually really cool to play with. What do you think would happen if I set beta to 0 in this? Like, what sort of behavior would you get? I will cold call because I know a few names here. Anybody? I don't want to cold call someone in my group.
You're going to get the shortest path.
Shortest path, that's right. Right? This term goes away. The cost is a function of the time. Shortest path. Now what's cool is, just one day I was messing around with this code. I'm like, I wonder what happens if I set alpha to 0. Right? So your cost is purely a function of uncertainty. Turns out, what the quadrotor does is it just hangs out where it starts. It says, I'm in no hurry, I know where I am, I'm just going to stay here. And so, but I find this amazing, right? Because this almost models behavior. You can start saying, like, do I want to be a risky quadrotor or a safe one? Like, how important is it for me to get somewhere on time or, be safe? And it's just those two parameters. Or you could even make it one, like alpha and 1 minus alpha. I think this stuff is really cool. All right, the one detail that I'm really going to go into for firm is the cost equation, which is based on the Bellman backup equation that we had. The cost to go, right, the expected cost from a belief state, cost to go from a belief state, is, well, you're going to take the best action, so you're going to take the min of this whole thing. You're going to say it's the cost of executing a specific action plus the cost of colliding with something, an obstacle, times the probability of colliding. Right? That's this term. And then you've got to say, well, okay, and then once I reach a state, what's the cost from there? And then I should weight that by the probability of ending up in that state. Does this equation make sense to people? Like, there are a lot of symbols, and honestly, I hate notation, but it works. You just plug in. The cost is, I'm going to take the best action. It's going to be the cost of using that action. The cost of colliding times the probability of colliding, given that I used that action. And I started where I started. And then the cost from where I end up. And since you end up in a probability distribution, right, you need to consider all those cases. Yeah?
When you define an action from one place to another, do you always think of it as starting from the mean that you've sampled, or from anywhere in the region?
So it's from so formally it was from the belief state, which is the mean plus, the variance once it's stabilized to that point. And the way that variance is generated, I should have said, is, right, you're going to have models of these quadrotors. And so you can, I spent a good time in the ACL with John Howe, course 16, and you just let the quadrotor hover, you measure its position for a long time, and you get, right, a distribution over where it goes.
So what is the letter M stand for?
What is the letter M?
Yeah.
Right, so you're summing over, these are the belief states that you could end up in. Right? So if everything were deterministic, this would just be, ignore the sum, it's where you end up. Realistically, you could end up in some other state. Have to consider.
So just a quick question. So those, if we're operating on continuous space and you have continuous observations, so those are sums over the observation samples that are generated so that is a finite sum over the possible infinite observation space that you might have.
Yeah, so there's definitely discretization in terms of where you could end up, and even the action space, there's a set of feedback controllers that you're allowed. I think the observation, if you modeled it as like Gaussian, if you make some nice assumptions, it can be tractable as continuous.
Oh yeah, I was just wondering, so for example, if you start with Gaussian noise and you have a linear model, then your prediction is going to be Gaussian.
Yeah.
But then if you have Gaussian observations, which is great because then your update is Gaussian, but the observation space is infinite. So basically, not only you have to sample positions, but you also have to sample potential observations that you might get as you go along.
Yeah.
So that you can basically, I mean, it's great, but you would be basically reducing a possibly infinite branching, which is your Gaussian, to kind of like a Monte Carlo tree search. You generate a whole bunch of meaningful samples, and those are the ones that you consider. So is that where the sum is coming from?
Yeah, I believe so. And a fun fact, the theorem that I read and trusted was that if you just sample randomly, right, from your configuration space, you have zero probability of constructing a graph that, without any assumptions, will be connected. Whereas for PRMs, right, you sample enough, things will turn out nicely. Not the case in the belief state. That's why we need to make these assumptions. Okay, we're killing it. We know Pom VPs. Now we get to look at some really fun graphics generated from real flights using Firm. Okay. The big takeaway is that Firm prefers safer paths. We've got two images that look really similar. I'm going to talk about one and then show why they're slightly different. The test flight that we put this quadrotor under was we said we're going to start at this configuration, we're going to go to this configuration, and there's this big blue obstacle. And there are landmarks that you can take measurements off of. So those are these red dots. We want to compare two planners, right? A PRM and a firm planner. The PRM planner said, right, I just want to minimize time, and so we found the shortest path is stay to the left of the obstacle, but that's actually a really narrow path between the obstacle and the wall. On the other hand, the firm planner said, right, I want to minimize the linear combination of time and uncertainty. And so if you ramp up the weight for uncertainty, at some point the path sort of pops over the obstacle. It's really cool, it snaps. And then you get this safer path. But that's longer. And how do we know it's safer? Because these ellipsoids that we've drawn are the 3D versions of what we saw for the PRM elevated to the belief space version. It's the uncertainty that the quadrotor has over its true state. Why is the PRM planner, why does it have such big ellipsoids? It's because when it's behind the obstacle, it can't make any of these measurements because it can't see the landmarks. So it's basically using dead reckoning, and the transition model, right, is non-deterministic, so its uncertainty grows. And so we can see these ellipsoids are bigger for PRM than firm. And then the reason I have two images is they are slightly different. It's that these landmarks were fictitious landmarks that we just said you can, and we would generate fake measurements off of them. And so we could tune the noise of the landmarks, maybe a little bit of cheating, but it allowed us to say, when we increase the noise from some dimensionless number 0.05 to 0.15, you can see the uncertainty ellipsoids for PRM grow when we increase the noise, whereas for firm they stay about the same. And importantly, these ellipsoids grow enough that they start overlapping with the obstacles. That represents a very high probability of collision. Whereas for firm, the way it managed to keep these ellipsoids so small is we kept the cost function the same, right? Same weight on the uncertainty, same weight on the time, right? But the uncertainty was so much higher. And so it would decide, well, I can sacrifice a little bit of time. I can take a slower path. I can just hang out by a landmark, really make sure I know where I am before continuing. And so the path, the duration of the flight took a lot longer for firm as time would increase, but the uncertainty would stay about constant. Do people understand these graphics? Great. All right. We've got a graph that just represents a little more formally that growing uncertainty. As noise increases, the variance along a single dimension, z, y, and x, for PRM, which is dashed, and firm. The variance for PRM is always higher and it grows. For firm, it's lower and it stays about constant. That's the big takeaway. And firm minimizes this uncertainty. And then the final image from these results that I want to show is in simulation. They said, well, let's actually measure how often it crashes. We didn't want to do this in the real world because you don't want to crash a quadrotor that many times. The gist of it is comparing a reactive planner and a deterministic one. As noise increases, noise was simulated with wind strength. The number of crashes increases for PRM, basically, and for firm, it stays constant and low. The reason there are two planners, or two lines, is there were two planners with different time horizons. The important thing is firm is low and constant, PRM grows. All right. We've talked now throughout all probabilistic planning you ever need to know, right? No, not quite. But we have covered a lot of stuff. What are the big takeaways? We've learned that real-world problems are stochastic, right? Quadrotors are not these perfect machines that we wish they were. That it's important to model them as stochastic. The problem is once you start modeling them as stochastic, it becomes a lot harder to solve. But if you make some assumptions, or even if you don't, if you're just smart and you use heuristics, you can resolve this complexity. And so I hope you remember these 3 points. You remember like this graphic or that graphic, the idea that if you take uncertainty into account, you can have fundamentally different paths and motion plans, and that can be a good thing. What questions do you have? And if you have, yeah. Sure.
So 3 questions. So far, I think people have 50% on the IRA problems. So how do you think, we can integrate the IRA problems into your firm? So for instance, we suggest, okay, this is the maximum amount of risk we want to take. Is it possible to integrate an array constraint into your optimization problem and solve it, or do you think it's something else?
So I imagine one thing that I would like to test is if we go back to our, this really crude version of our cost equation. We could imagine saying, like, if we want to come up with a bound for uncertainty that we can tolerate, you could imagine maybe like setting the intercept for this to be that bound, and then just ramping this up.
Oh, I see. You mean act as like launching a multiplier and solve the optimization.
Something like that. Yeah, exactly. So it only comes into effect. Possibly what I said is a terrible idea, but like it's, especially in simulation, you should just try it out, see if it works.
And there's another question that you said, propagate the probability distribution along the network so hard. I don't quite get it because you have a state A, B, C is discrete, so it's more like a multinomial distribution. So therefore, you can assume like a Dirichlet barrier, and then Dirichlet barrier and the multinomial distribution they are contribute to each other. Therefore, you can by keep adding the observation and then update your barrier then form a posterior distribution, right?
Sure. So I think that might be making some assumptions that you might not be willing to make about the nature of the distributions that you're trying to propagate. I'd need to think about this some more. But I think intuitively we can understand that anytime you're propagating a distribution versus a single discrete value, it's definitely not going to be easier. And so as your distributions become more complex, perhaps if you're modeling a real-world stochastic sensor, you might not be able to perform these efficient updates using conjugate priors or something like that. Any other questions? Otherwise,
So all these firm examples are showing, this is all planning done offline, or you're doing this offline, right? And have you expanded this at all into like an online case, or does that all require replanning, and how long does it take?
Right, so it's not good, I can tell you that much. What's nice is Firm generates a policy. So if you construct your PRM to say, don't just find the shortest path, like keep sampling points until you're confident that you're always going to end up near some point, you can construct a policy and then just online look up what's my belief that matches most closely. It took I think we sampled 600 nodes in what are the dimensions on this? It's a 3 meter by 8 by 3 meter thing. It took about 15 minutes. It was really slow. Granted, it was a virtual machine, but it's not something you want to replan on the fly, whereas PRM is typically a lot faster.
But what's a lot faster in that case?
So when we just did PRM, I think it was 1 minute or something, at least in order of magnitude. And you could use other planners as well, like RRTs, and there are RRT versions there are POMDP versions of RRTs, but I haven't commented on those. All right, I'm going to turn it over to Steve so we can learn about this project.
About the grand challenge. So the final assignment will be released tonight for this. And as Professor Williams mentioned, it's going to be de-scoped a bit from what we originally had in the syllabus due to time constraints, but here's a preview of what you'll be doing. So for an overview, it will be a class-wide collaboration. So what we're going to do, you guys are going to stay in your advanced lecture teams and each basically apply what you've done, the great work you've done on that, onto our hardware robot that we have. So it's not a competition where each team will be competing against each other. All right? So again, and we're de-scoping it. The syllabus originally said it would be 20% of your grade. It's probably going to be more like 10 or 15% in the end. So this is the robot you guys will be using. It's called an X-Worm robot. Usually it has sort of a robotic arm on it, but we're actually not going to be using it for this set. It's this base made by a company from Spain, Robotnik. It's a pretty cool robot. One cool thing about it is that it's actually omnidirectional. So there are wheels on your wheels here. And what that means is that it can drive sideways, left and right. It would make parallel parking your car very easy for we're not going to be driving it probably this fast because it's actually super heavy and we don't want anyone to... Yeah, we forgot to screw in the we'll be screwed in during the competition. But it's a pretty fun robot, so you guys will be working on this. And so the actual challenge itself, as we've mentioned many times throughout this class, will be a modified orienteering challenge. So there's going to be a few different challenge stations that you have to drive to. And at those stations, there'll be small computational challenges. And those computational challenges will be a subset of the advanced lecture teams, not all of them. And the goal is to complete as many of those as you can and try and sort of do that as quickly as possible. And it's also going to be held indoors in our lab space where we just showed you, so that way if it rains, we can still have the grand challenge at the end of the semester. So this is sort of how it's set up as of last night, actually. So basically, it's a robot that'll be able to drive around a small little Lego maze that we've set up. And there's going to be sort of different things that you have to do at the different places. So what are you actually going to be doing? What assignment are you guys going to be doing? Well, it's actually a little flexible. Since each of you did different things for your advanced lectures, you're all, each team is going to have a bit of a different assignment applying it to this. I have some proposed ideas that I'm going to talk about in the next slide here. But the big thing is that these are just ideas. You guys have a lot of flexibility in this. You'll be probably working with the core staff a lot to have access to the robot. We can arrange extra office hours for you guys to come use the hardware, to test things. So we'll be arranging all of that things as sort of on an as-needed basis. If you want to sort of, basically, it'll sort of depend on your team.
And the people who will be helping out are you?
Yeah, me and Tiago, who gave a lecture earlier in the semester, and possibly also a few other people from our lab. That will be the main contact points for it. So, of course, it should go without saying, but all the team members should contribute equally within your team. So it'll be a little bit, maybe less structured than an advanced lecture, but just make sure that everyone is contributing equally to the assignment. And it's going to involve using this thing called the Robot Operating System, or ROS, which is basically a software framework for communicating, and it's used a lot in robotics. Just a quick show of hands. How many of you have used ROS before? Oh wow, so a lot have used ROS. How many have heard of ROS, if not used it? So, okay, so a lot of people. So that's a good starting point. So here are the proposed tasks for each group, and of course all of these are up for change. If you guys want to change it, let me know. Basically, so some of the groups, it's very clear how it would immediately apply to the grand challenge. So, incremental path planning. Well, we have a mobile robot, so maybe we can actually put that on the robot and get it to, change your plan if something gets in the way. The semantic localization group, obviously, very applicable to the grand challenge. You need to know where you are. So the robot that we have now can actually do normal metric localization, so it can sort of know where it is. But what would be interesting to see is compare the semantic localization to that one. But how would you do semantic localization? Well, we can use a camera, and we can use the visual learning through deep classification, the visual classification through deep learning group. So I think these two groups would have a really nice synergy and a really cool way to work together. So the MCTS group, very cool, but I had a little trouble thinking about exactly how that would apply. So maybe you look like you have an idea, maybe.
So yeah. To clarify, all of these are separate runs of the robot?
So we're actually probably going to run all of them, and this would be probably one run of the robot. We're going to decouple these so that if one or a subset of these don't work super well, the other groups will still be able to run. So we're carefully planning that out too. So the MCTS group, I was thinking maybe could solve, that could be a really nice way to, one of those computational challenges. Maybe you have to play against a human, and if it wins, great, you can go faster or you get more points. So you could implement it on a different game other than Connect 4, or possibly, and sort of wrap it around ROS to call it that. The reachability group, I think, would also be a great place to do one of these challenge stations. So we could give you guys sort of a puzzle, say maybe sort of some sort of maze-like state space, and you have to see, could you even reach the goal here? And if you get the answer right, well, you can move on to the next stage or get more points or something like that.
But again, these are just suggestions. So, for example, they can do the reachability for doing motion.
Yeah, so if you guys have other suggestions on how to implement your team stuff into the Grand Challenge, definitely send me an email, preferably today or as soon as you think of these things, and we can change these. These are just suggestions for right now. The last two are sort of more planning related. So planning with temporal logic, which was Monday's lecture, I thought would be a cool way to sort of control the robot's high-level action. So maybe that could involve modeling our Grand Challenge with P2DL, and maybe with linear temporal logic goals, model the Zebbuki automata. Then you could compile that and call a planner on it and execute that plan on the actual robot. So it would be controlling the high-level actions of the robot. That's a possibility. And for today's group, the Infinite Horizon probabilistic planning, maybe you could do something actually sort of similar, but instead of modeling the domain as P2DL, model it as an MDP and solve it with LAO star and get sort of a policy on how to control the robot. Maybe we can change it a little bit to certain squares can be more risky than others or so on. So again, there's flexibility in all of these here. So these are just some of the suggestions. Does anyone have any questions before we? This is all I have. So anyone have any questions? Yeah.
How are we working on code together? How are you going to figure it out?
So it's basically up to you guys really to divide up the work amongst yourselves. It's really different for every team. So
each team is developing separately their own package.
Right. Yeah. Each team is developing their own separate package. For example, these two teams, there's probably going to be a common interface where the output of this one goes to the input of that one. So for that one, we're going to give you sort of the interface, namely a ROS message type package for that. But other than that, like for dividing up the work, you guys are really on your own for that.
So your plan is well taken. Integration, if you're trying to integrate all the pieces that the group is doing, then it's entirely time-consuming thing that uses software engineering skills, not the kind of skills we're doing in here. It can be really unpleasant to do, and it can take a lot of time. So we don't want you to have that experience. Right? So that's why you can. Not only what we want you to do is to be able to get your own capability, trying to leverage off of ROS to have to interact with the robot. If you guys choose to integrate with other teams because you are really excited by that and because it looks like they're people that you're working for and it'll be smooth, then that's purely your choice. Okay? Is that fair enough?
Sure. Any more questions? Okay. And